Hi, this is Forrest Fowler, and this is my first Tier 4 project for the Newton's Laws of Motions. So the first thing I'm going to do is I'm going to explain an accelerometer. Now, an accelerometer is it's a device like this. It's just a jar filled with water, and it has a little cork in it right here. Now what happens is that when you accelerate the jar, the cork moves towards the motion of acceleration. And the reason it does this is because of the different inertias. So I'll just demonstrate that real quick. So I'll move this back a little, and as I accelerate it, well, that didn't work, but theoretically, it should move it forward. You saw it a little bit there. It's kind of hard to see in the skippiness of the video. So the reason is that is because the different inertias. So the way you can tell there's the different inertias is that the cork for one floats. So an inertia is just another way of saying mass almost. So since or density, excuse me. Well, mass also. So because the cork is floating, it has a lower inertia. So what that means is that when this starts accelerating, the water moves further back in the jar because it's accelerating and because the object around it's accelerating faster than the water is. But the thing is that the inertia of this is less than the inertia of the water, so that displacement of the water pushes the cork further forward. So just like the gravity is pushing down on the water and the displacement is pushing the cork up, when the acceleration is pushing the water backwards, the displacement will push the cork forward. So that's just a really simple way of explaining how an accelerometer works. So the difference between off of that, I will go into the difference between inertia, mass, and weight. So weight, mass is how much matter there is in a substance. That's the easiest way of explaining it, is how much stuff there is. So weight is actually a measure of the Earth's gravity, where Fw, which is weight, is equal to mass times the gravity of that particular of the particular location. So that's why weight varies from planet to planet, but mass never does, because mass is a constant. Um, and with that, what inertia is is a how much mass is in it, but it plays off of density a lot. So it's kind of like how much mass is there, but it also plays off of density at the same time. I don't know if I'm supposed to use this marker, but it's slightly coming off, so I'll just assume I am. Okay. For the next thing I'm going to do the submarine. So a submarine is submerged at 50 meters below sea level and draw all the action-reaction parts of the system. So basically a free body diagram. So if we have our submarine right here, this is the sub. Can't really see that. Let me get a better marker real quick. Okay, I'm back. And this time I have a better marker, hopefully. Okay, so we have, there we go, our sub. So we'll just assume for the sake of the problem that it's not moving at the moment. So it's 50 meters below the sea level, and we have to draw all of the reaction diagrams. So what we have right here is we have gravity pulling down on it, and that is represented by mg. So that's pulling the sub down towards the bottom of the ocean. But what is pulling it back up is the normal. And what the normal is that Newton's third law states that every action has an equal and opposite reaction. So if I push something, it pushes me back, And that's why if I push off of something with a greater inertia than me, I ended up getting pushed back. So if I push off a wall, I end up moving and not the wall. So how that works with gravity is that there's always the normal. And what the normal does is that as gravity is pulling it down, the gravity of the sub is also pulling back on the Earth. And that's what causes the normal to happen. So that's the action-reaction pair of the submarine. Okay, so let's do the last problem for Newton's laws. I don't think I'll get to 10 minutes, but this includes all the problems that I had, so sue me, McNeil. Okay, so it says, according to legend, a horse learned of Newton's laws. When the horse was told to pull a cart, it refused, saying that if it pulled the cart forward, according to Newton's third law, there would be an equal force backwards. Thus, there would be balanced forces, and the cart would not move, according to Newton's second law. How do you reason with this horse? Okay, so let's draw the free body diagram for both of them. So we're going to have the horse. Let's draw the horse. I'll just represent that with an H. And then since it's a free body diagram, the one rule is that we have to draw all factors affecting it. So that includes the gravity, that includes the normal, that includes the force of it moving forward, and that includes the force of it going back. So for this, it'd be friction. So we'd go with mu k pulling back, because it's the kinetic friction pulling back. But what's actually pulling it forward is the mu s, the static friction. It's the static friction of the hoof being placed on the ground and pulling it forward when it walks. So then let's draw the cart, and that will be a C. It's a little close, but I'll make it work. So we have gravity, we have the normal, we have mu k, and we have mu s. Okay. So these mu k's are equal because it's the kinetic friction of the cart pulling on the horse, and these mu s's are equal because it's the static friction of the horse pulling on the ground, which then pulls on the cart. So the question is how are we going to explain to the horse that it'll end up moving forward? And the answer is really simple once you get to this part, because kinetic friction is always greater than static friction. That is always a constant. So the static friction of an object on another is always going to be greater than kinetic friction. So when it's pulling its hoof across the ground, that friction and that force forward will be greater than the kinetic friction, which would be less. And that's how you would explain to the horse that it would actually be pulling the cart forward and tell it to get back to work. So I got about 8 minutes here, but that's all I have for Newton's laws, so whatever.